Okay, so we're going to continue with 14.2, and we had left off with this exercise. So our goal again, which I already stated, was to show that the limit in this case does not exist. And so recall that we had primarily one method where we had two paths, which ended up giving us two limits that were different. And so let's try a couple of paths here. Let's try the simple, x equals 0, which is along the y-axis. So we have limit y going to 0 of 0 divided by 0 plus y to the 6th, and that's 0. Similarly, you can check if you set y to be 0, then the limit will be 0. Okay. Let's try one of the lines. Let's try y, a general line, y equals mx. Well, we have xy cubed over x squared plus y to the 6th. So x and then mx cubed over x squared plus mx cubed, mx to the 6th, sorry. So what do we end up with here? We have m cubed x to the 4th divided by x squared plus m to the 6th, x to the 6th. And so we can factor out, so we're taking limit here as x goes to 0, by the way. Forgot to write that. We have limit x going to 0. So limit x going to 0, and you can factor out x squared on the bottom, and this becomes m cubed x squared divided by 1 plus m to the 6th x to the 4th, where x is going to 0. And now this, well, this goes to 0 over 1 plus 0, which is 0. So along any line, the limit is 0. But that still doesn't show that the limit is actually 0, because we still have a lot more types of paths. And so if you do a little bit of inspection, what we're going to do here, and I'm sorry, I think I have, yeah. So what we're going to do here is we're going to set x to be y cubed. So this is a path in the xy plane. So x equals, so here's x, right, here's y. And so this is this curve, right? And, well, it passes through the origin. So it's a path that passes through 0, 0, so we can use this path. So let's start here with the original xy going to 0, 0 of xy cubed over x squared plus y to the 6th. So this becomes the limit. If we put x equal to y cubed, we're going to have limit y going to 0. We're going to have y cubed times y cubed divided by y cubed squared plus y to the 6th. And what we get here is y to the 6th over 2y to the 6th. Oops, with the limit. Let me rewrite that. So we have the limit y going to 0 of y to the 6th over 2y to the 6th. And this is 1/2. And that's different from 0 because all the other paths gave 0. We got different paths leading to different limits, so hence the limit overall does not exist. Okay, so this is another example of a limit not existing. Just a little remark here, which hopefully is clear, but I didn't really mention it. If I just put limit of xy going to some other value, say like, -1, 0 or something like that, of xy cubed over x squared plus y to the 6th, the function here is continuous at that point. So note this thing is continuous at -1, 0. There's no singularity, so you can just plug this in, right? This is just negative 1 times 0 divided by negative 1 squared plus 0 to the 6th, which is just 0. So by continuity, you can just plug in the value. The only problem is where you have these singular values where you're dividing by 0 or something like that. Okay, let's consider another example. And now what we're going to do is we're going to try to show, in a way this is kind of a different example, we want to now start showing limits exist. Showing limits that exist. Okay, and there's essentially, at least at this stage, is mainly two methods. One is to switch over to polar coordinates. And the second one is to use factoring. And in this video, we're just going to talk about the polar coordinate example. In the next video, we'll do the factoring. So our example will be as follows. Let's take the limit as xy go to 0, 0 of x squared y squared over x squared plus y squared. So the idea, and normally this is kind of, if you see, so what is the strategy here? The idea is if you see an x squared plus y squared type term, or something where you can factor and you get an x squared plus y squared, then we can switch to r being, not r being, but x being r cosine and y being r sine of theta. And that's what we're going to do here. So let's plug in these substitutions, and remember that if x and y are going to 0, this is the same as r going to 0. Remember, theta is kind of always rotating. Theta is rotating. So theta going to 0 doesn't necessarily mean you're going to the origin. R going to 0 means you're going to the origin. So what we get here is we get the limit as r goes to 0 of r squared cosine squared, r squared sine squared, divided by r squared cosine squared theta plus r squared sine squared theta. And recall that the bottom here is just r squared. So this is the limit as r goes to 0 of r to the 4th sine squared cosine squared divided by, you can factor out the r squared and you get cosine squared plus sine squared, and hence the denominator is just r squared. So remember, sine squared plus cosine squared is 1. And then you can cancel a couple of these r squared. So we get limit r going to 0 of r squared sine squared theta cosine squared theta. And then note that theta can be any value. Theta can be any value here. Right? We're not really sending theta to a particular value because theta is just a rotational parameter. So what do we do here? Well, note that 0 is less than or equal to r squared sine squared theta cosine squared theta, which is less than or equal to r squared because sine and cosine are at most 1. Sine squared and cosine squared are also at most 1. And if we sort of take limits here, so this just stays as 0. This is less than or equal to the limit r goes to 0 of r squared sine squared theta cosine squared theta, which is less than or equal to the limit r going to 0 of r squared. Well, this goes to 0, and so sort of by what's called the squeeze theorem, this must go to 0 as well. So hence the limit of xy going to 0, 0 of x squared y squared divided by x squared plus y squared, this equals 0. Okay, I'll leave you here with an exercise which is somewhat similar. So consider the limit of xy going to 0, 0 of x squared y cubed divided by x to the fourth plus y squared x squared. And so you're going to try to use polar coordinates to find the limit. Now before I end here, I want to make one remark here. Sometimes it doesn't work out. Like for example, in our one of the original examples we started off with was xy over x squared plus y squared. And now this has an x squared plus y squared, but we showed that this limit doesn't exist. But let's just say we used polar coordinates. If we switch over to polar, this becomes a limit as r goes to 0 of r squared cosine theta sine theta divided by r squared. X squared plus y squared is r squared. And this becomes the limit as r goes to 0 of cosine theta sine theta. Now, the moment you see something like this, where the r's have gone away, it's very likely that the limit does not exist. Because notice this doesn't even depend on r, theta can be whatever value it likes. But still, if we want to formally show that the limit does not exist, we need to select two paths. So sometimes something may look like the polar coordinates is going to work, but then it doesn't. And when it doesn't, that's indicative of most likely a limit that doesn't exist overall. So just because there's an x squared plus y squared doesn't mean you're going to be able to use polar coordinates successfully to show that the limit exists. So I just wanted to mention that before ending. In the next video, we'll start off with this exercise, and then we'll go to the factoring method of showing limits exist.